This is now the third video in the Directional Properties of Crystals lectures, and in this one I'm going to talk about fourth rank tensors. So fourth rank tensors, they're the ones you need for the elastic moduli or the compliances. And they map strain into stress. Here is the elastic moduli. You multiply the elastic moduli times the strain and you get the stress. Now, of course, since both stress and strain are matrices, tensors, you need more tildes above the C in order to do the mapping. So here's the moduli or the stiffnesses. Here's the other way around, where the strains are a function of the stresses, with the constants of proportionality being the compliances. We could write this in index notation with the Einstein convention, where the stress in the ij type is going to be equal to a strain in the KL direction mapping through the Cij KL. So again, there's the Einstein convention. Since we have in general 9 components in the stress tensor and 9 components in the strain tensor, that gives us mapping of 9 times 9 coefficients, or 81 coefficients. But we have already noted that stress and strain are each symmetric, thus there are only 6 independent coefficients, and thus only 6 times 6, or 36 coefficients, are needed in theCijkl tensor representation of the stiffnesses. Now we'll use a Voigt convention to label the 6 independent coefficients in either the stress or the strain tensors. And here's how you do that. Go down the diagonal with 1, 2, 3, and then circle around counterclockwise for elements 4, 5, and 6. Thus, indices 1, 1 maps to Voigt notation 1, 2, 2 to 2. The 2, 3 index goes to Voigt notation 4, and so on, down to 1, 2 going to Voigt notation 6. So we can recast stress and strain, which are tensors 3 by 3, into a 6-component pseudo-vector. So here it is, sigma with all the stress components laid out as a column vector, and there's strain also as a column vector. Cast in this light, we can map stress into strain with a 6 by 6 matrix of coefficients in this form, where the matrix multiply of that 6 by 6 times the strain will give us the stresses. Now I'll point out that I have created this array of numbers that in a symmetric fashion, and so there are only independent coefficients as highlighted in yellow here. So everything in the lower quadrant is simply a transpose of what's in the upper quadrant. You count all the available coefficients in the upper quadrant and you'll come up with 21 independent coefficients. I'll also note that this matrix representation for the elastic constants can be inverted to give either, well, invert stiffnesses to get compliances, or invert compliances to get stiffnesses. In MATLAB, this is a simple command of S is equal to the inverse of C. So why is this elastic moduli matrix symmetric? Well, we can look at the energy change relationship. The work done in elastic strain is simply a force times a displacement, or a stress times a strain. We can substitute in Hooke's law, our generalized formula for stress, and that gives us the change in work is proportional to the stiffness coefficients times the strain in the jth direction and the differential in the ith direction. Now we can rearrange this in this form where we have the change in work in the strain I direction is equal to the elastic constants tensor matrix times the strain in the jth direction. At this point, we can take another derivative with respect to strain on both sides of the equation. It looks like this. Perform the operations, and we have a second derivative of energy with mixed directions I and j is equal on the right-hand side to the coefficient of the matrix Cij. So first observation is the elastic moduli are second derivatives of the elastic work with respect to strain. And since work, or is energy, is a exact differential, the order of differentiation cannot change the answer. Thus, both stiffness is Cij and compliance is Sij must be symmetric in order for that equation to be true. Let's talk about coordinate change for fourth rank tensors. For generalized second rank tensors Q mapped into P by a fourth rank tensor T, remember that the second rank tensor is transformed with coordinates by application of the transformation matrix twice. Likewise for Q. So it's no surprise that it's going to take 4 applications of the transformation matrix in order to transform a fourth rank tensor. Here is the Einstein summation notation for the transformation of a fourth rank tensor T into primed coordinates using transformation matrix A. I have a custom MATLAB function called rotate Cij, which will perform the rotation as described in that equation. Now remember that the 6x6 representation of elastic constants was a convenience for mapping the unique elements of stress and strain into each other, but the 6x6 is not a tensor. So therefore, we need to convert the 6x6 into a fourth rank tensor, a 3x3x3x3 array of numbers, before we can rotate it. The tensor form is rotated as shown above, and then the tensor form can be back converted into a matrix. Rotate Cij is fairly flexible. If you give it a matrix, it will convert it to a tensor, rotate, and convert back. If you give it a tensor, it will rotate the tensor and return the tensor. Within rotate Cij, I have a function t to m, which converts matrices to tensors and tensors back to matrices. Let's talk about some examples. So first, we're going to create a 6x6 array using make Cij. The arguments are the set of elastic constants in a vector and the symmetry that you wish to use as a string variable second. So tri with quotations around it is a string vector for triclinic. 1 to 21, 1:21 is a vector of elements 1, 2, 3, 4, and so forth up to 21. This function will return this matrix. You'll see that it has 21 unique elements and it's symmetric, so across the diagonal the elements are flipped, and the numbering scheme starts off by going down the diagonal. Now, just to show that make Cij is flexible, I feed into make Cij the matrix representation, and it's going to return a vector C, which is what we originally put in, numbers 1 to 21. Let's look at what happens when we make an orthorhombic elastic constants matrix. So O for orthorhombic, there are 9 elastic constants, so I feed it a vector 1 to 9. And that'll give me this array of numbers, where again we count down the middle, the diagonal, and then go to the off diagonals C1, 2, 1, 3, and 2, 3. So you notice that I've ordered the set of elastic constants in a specific way, but as a vector. Now there's no unique way to do that. Another common way of doing it is by cyclic permutation, first on the second index and then on the first. So let's apply symmetry operations to our matrix representations of the elastic moduli. We start with the most general triclinic constants, 21 constants symmetrically arrayed about the diagonal. Let's just take one mirror plane, the YZ mirror plane, and that would be created by a transformation matrix of this form, which reverses the sign of x but leaves y and z alone. If I rotate my most general triclinic constants about that rotational transformation, I'll get a prime set of elastic constants that look like this. And you'll notice the only difference between this and the original is that we've switched the sign of a number of elements but left them in the same place. Clearly, the only way a number can be equal to the negative of itself is if it's 0. Thus, constants in the locations 9, 11, 12, 13, 15, 17, 19, and 20 all must be 0. You can apply additional symmetry operations to further reduce the number of elastic constants for specific symmetry systems. Make Cij will give you the form of the elastic constants. You tell it you want an orthorhombic set of constants and it'll have the right form. You tell it a monoclinic, it'll give you the right form. What I want you to do is use symmetry operations acting on the triclinic matrix to determine what the correct form is for monoclinic, hexagonal, orthorhombic, and cubic crystals. And that ends this video.